welcome to this explainer. Okay, so we're going to decode a fascinating mystery today. How on earth do astronomers figure out the bizarre, stretched out, and totally deformed shapes of asteroids when they're so incredibly far away? I mean, through a telescope, they literally just look like tiny single dots of light. A lot of us probably picture asteroids as these perfectly round space rocks just casually drifting along, right? But the reality is way weirder. As we map out our solar system, we're finding elongated ones, flattened ones, and some that look straight up like two objects got smashed together. Let's get right into it. So, that brings us to this massive cosmic puzzle. If asteroids like 433 Eros or 101955 Bennu are basically just invisible distant pixels to most of our telescopes, how do we actually know what they look like? It sounds completely impossible, but scientists have developed an incredible toolkit to solve this, and it all starts with a surprisingly simple idea. Section 1. The secret in rotation. Our very first method relies entirely on just watching how an asteroid behaves as it spins out there in the dark. It's all about how it catches the sun. Think of a stretched-out asteroid like a giant spinning space potato. As this huge rock tumbles through the void, different sides reflect different amounts of sunlight back toward Earth. So when its wide side faces us, it catches more light and naturally looks brighter. But then, as it rotates and shows us its narrow side, that brightness dips. This continuous up and down pattern gives astronomers a predictable graph, which is known as a light curve. By meticulously tracking this cosmic rhythm, astronomers can pull an amazing amount of data. They can figure out the exact rotation period, how fast the asteroid is spinning, and get a real sense of its degree of elongation. The main takeaway here is that a massive difference between the maximum and minimum brightness on that graph means you're dealing with a highly irregular asteroid. Just from watching a single dot of light get brighter and dimmer, we can literally sketch out its basic proportions across millions of miles of empty space. Moving on to Section 2, the mathematical puzzle. Now we step it up from basic observation to some serious computational power. Okay, so while a basic light curve just looks at a single rotation, this next technique, light curve inversion, is vastly more sophisticated. This method tracks the asteroid from all sorts of different orbital angles over months or even years, as both the Earth and the rock move around the solar system. Then computers step in to do this wild reverse engineering process. Instead of taking a known shape to predict the light, they mathematically work backward from years of brightness data to reconstruct a highly probable 3D shape and its axis of rotation. And this heavy inversion math has proven the existence of some truly bizarre structures. It revealed incredibly elongated objects, like the asteroid 1620 Geographos, and these fascinating things called contact binaries. A contact binary is literally just two separate rocks stuck together, like the asteroid 25143 Itokawa. Now, this math might not show us tiny surface craters, sure, but giving us a highly accurate, global 3D model from billions of miles away, that's a huge win. Section 3. Astronomical radar vision. To see all those missing surface details we just talked about, we just have to wait for an asteroid to swing a bit closer to Earth. Enter astronomical radar. By blasting radio waves from massive radio telescopes at a passing asteroid, and then measuring exactly how long it takes for the signal to bounce back, along with the frequency shifts caused by its spin, our resolution gets a massive upgrade. Radar lets us map actual surface features like craters, mountain ridges, and flat plains. We can even spot tiny little moons orbiting the asteroid that were completely invisible before. Section 4. Shadows and stellar occultations. This next method takes a wonderfully elegant approach, using the light of distant stars. This phenomenon is known as a stellar occultation. Basically, from our perspective down here on Earth, an asteroid will perfectly align in front of a distant star, completely blocking its light for just a few seconds. To catch this, you have multiple observers stationed all across the globe, and they perfectly time exactly how long that star goes dark. By piecing together all those individual shadow measurements from different locations, astronomers literally connect the dots. They reconstruct the exact contour of the rock by drawing its shape entirely out of shadows. And finally, Section 5, Real Encounters in Space. The absolute climax of our mapping toolkit requires us to pack up and leave Earth altogether. Space probes sent by NASA and JAXA have finally given us breathtaking, up-close reality checks. We now have actual, high-resolution photographs of asteroids like Ryugu, Bennu, and Itokawa. These modern, real-life visuals reveal details we could never even dream of seeing from Earth. Physically visiting these specific asteroids has completely transformed what we know about these small worlds, giving us the ultimate cosmic ground truth. And you know what? Direct observation revealed a completely shocking truth about our solar system. Instead of being solid, unified chunks of rock, monoliths, many asteroids are actually incredibly fragile structures. They're basically just giant blocks and deep craters acting as flying piles of cosmic rubble. And crazy enough, they are held together by nothing more than their own very weak gravity. It's just incredible to think about. Decoding billions of years of history, ancient collisions, and the actual formation of our solar system all started by simply analyzing tiny variations of a single dot of light in the night sky. Every bulge, every crater, and every weird elongated shape tells a story that has been 4.5 billion years in the making. So as our tech keeps getting better and our maps get even more precise, we have to ask ourselves, what other ancient secrets are quietly waiting for us in the shapes of those distant rubble piles?